Oh,
Good day. My name is Evgenii Grigorev, and my today's presentation on OpenMic would be about LLM-powered coder assistants. So what is it? What is this coder assistant and how they work? Well, they are based on LLMs, or large language models. This is some kind of large neural network that tries to predict some words. Here you can see some very simplified example on how it works. Here we have some words as input and we have some output words. Basically, we have something like 50,000 words as input on the input layer, and we're trying to guess one of the 50,000 words on the output layer. The problem is that there are a lot of connections between these layers, like 50,000 squared. That's a lot, and we want to avoid it because that's just a one layer, and that's already a lot of connections. So this is not really optimal. It will take a long time to work. It will take a long time to train, to backpropagate. Then we have to make a lot of different layers for this, so it will take much more time. And this is really not an efficient way to work with it. I hope everyone here is familiar with how the neural networks works. So the next slide would be about encoders and decoders. We are trying to reduce the number of the connections. So actually, we do not care about the exact word which is used. For example, we can try to guess the word in sentences like the king sat on the something, the queen sat on the something, the princess sat on the something. We do not actually care who sat, the king, queen, or princess, because we all know about the concept of royalty, nobility, and something like that. So we can guess that if they're sitting on something, well, that's probably a throne. This may not be so intuitive for the LLM, so we are using something called encoders and decoders to extract these conceptions from the words. Basically, we are taking some token and using some neural network that will convert the word in the combination in some vector of size 256 in this example. And then we're using another neural network to convert this network to some word, which would be used later. And with this, basically, we can fine tune it so the words with a similar meaning, like king and queen, will have vectors that are pretty close because they share some kind of conceptions between them. Of course, we cannot exactly tell which conception is extracted from our words because it's a neural network, but it may be something like nobility. Is it animated object? Is this old? Is this made from stone or something like that? So here we have drastically reduced the amount of the connection between the layers, because on this part we have like 50,000 times 250 connections, and we have another layer like this. So it's basically 50,000 times 250 times 2, or about 100 times less connections than, for example, here. So that's quite useful. But we are trying to predict only one word based on the one word in input, which is not really interesting. So we can try something called masked language models. Basically, we are trying to predict some sentences based on some input sentences, which has some masked word in it. So here, the something set on the throne. And we can consider these generative models as a kind of subset of these masked language models. Like if we are trying to predict the last word in the sentence. So the something, then this input is used for generating the next prediction, then for the next prediction, for the next prediction, for the next prediction, and so on. That's why this model is also called autoregressive models, because it uses its own output as its own input. But it is not so easy to make this connection between all these words, because the words in the sentence have some connection between them. And for that, we are using a concept called self-attention. Basically, it makes sense that all words in sentence make some connection within them. Like, we have some sentence: the alien landed on Earth because it needed to hide on the planet, and we can see the connection between word it and alien because it's pronounced. We can see some connections from the point of syntax, like subject, verb, object. You can see the words that share some similar context or concepts like planet and Earth. So our main task becomes how to actually compute this self-attention, like how each word is connected to each word in our sentences, so we can actually predict better. Well, that's how it's computed. First, we encode all the words or tokens and take the 4 copies of it. One is set aside, and we will use it later. Then we will recompute 3 of them and call them query, key, and value. If you know about hash maps, hash sets, or something like that, it may sound pretty similar because, well, it is similar in its concept. Then we are trying to compute similarity between the query and a string with a dot product, and with it we will get some metrics that will show our attention scores between which will show the attention scores between the similarity between the keys and queries. Then we will multiply this matrix by the values of the encodings, which will in fact make some mixture of the words, like mixing of their concepts. And then we will add the mixture of the word to the original word, which can be used later to enrich its representation. Here you can see is this visual representation, like we have some hash map, which has some keys, which are encoded values. We have some values, and we have a query. We are basically comparing the similarity between these vectors, creating this matrix between them, and multiplying it by its values. The next part is tokenization. Before that, I said that we are encoding words, but it is not completely true in all cases. We may encode in with different kinds of tokenization. Like, we can encode each word as a different token. We can encode some parts of the words like unbelievable, because un means like no, which is maybe useful too because it has its meaning in it, not in the whole word. And we can try to make a shared character-based tokenization to encode every character, which is not so much useful as, for example, subword-based tokenization. Well, and this presentation is basically mostly about the code assistant. So, how is it exactly trained? Mostly, it uses some GitHub scrapes to train on the GitHub data. Basically, at first, it starts collecting some data from the GitHub using some web scrapers that are parsing some public repositories to get data from this. Then it comes with tokenization and preprocessing. Basically, we are making some filtering in data, making some variables anonymous, because we don't want their names to influence our predictions, because it may introduce some bias in it. We are introducing some tokens from, as I said, mostly from the keywords, from the name of variables, from some operators like division or multiplication, something like that. Then the code learns the code patterns, like it has to learn how the function looks like def, fun, some arguments, return, and so on. It learns that if we have some if, then it's probably that else would be somewhere nearby. If we have try, then cache should be somewhere nearby. Or it will learn some commonly used patterns, like if we have something like import pandas as PD, then we should expect something like PD read CSV, something like that. Then comes filtering for quality and security. Basically, we are trying to filter out some data which contains some bad code practices for it, using some static analysis or some human feedback that will actually punish the neural network for using the bad coding practices for the generated code. Then comes concept-aware fine-tuning. Like, we all know that neural network is using a lot of code for its education, but it may not be all useful for us for cases. So we can fine-tune it for it to work better for some specific task, like adaptive prompting. Adaptive prompting, which will adjust the output based on the concepts that user provides. For example, it will provide the answer in different languages. If we ask it to generate code in Python, it will generate code in Python. If you ask to generate code in Java, it will generate code in Java, and so on. Then there is reinforcement fine-tuning, which is basically connected to the human interaction. Like, human can often put likes on or dislikes on some answers of the neural network, so it gets some penalty if the user don't like its answer, or it can get some penalty if some code analyzer shows that the code is buggy. For example, if you have some for which does nothing, or if you have some infinite loop, or it will give some rewards if the code is good. And there is contrastive learning that basically helps with generalization. That's some examples of how it can generate code, basically of analyzing some time series depending on different inputs. That's analyze stock trends using moving averages. It is identify seasonal temperature trends. And this is predict machine failure probabilities using logistical regression. Again, this is all tasks about processing of time series, so it has some variability in it, and the machine has to take into account our context, like the exact our wording. What do we need from it exactly? How this actually evaluated? For example, in CodeX paper, they've used human eval benchmark. Basically, it consists of some coding challenges that require model to generate some code based on some docstring, which describes what it should do. Here's some example of it, like separate parentheses groups. So as you can see, this is not a hard task at all. This is pretty trivial. But this Codex neural network that is actually used in GitHub Copilot solved it like only 28% of all cases on the first try, which doesn't sound good, but GPT-3 haven't solved it at all on the first try. But if you try to take more samples from it, it will gain much higher accuracy, like it will have 70% success rate. Another problem with these neural networks are hallucinations, hidden biases, and copy-paste paradox. Hallucinations are pretty simple concept that the neural network may start making some really weird things, like it may made up some connection between some relationship between moon phases and stock prices if it will take a look on our data, which does not make sense because first, correlation doesn't mean causation, and second, there may be no correlation at all. It may just made it up because, well, it seemed somewhere that there are some correlations, we have some moon phases, we have some stock prices, so there probably should be something like correlation between them. And from it starts hallucination further and makes assumptions that moon phases and stock prices are connected. Another problem is hidden biases. So if you have trained on some specific data set, this data set may influence our results, because, for example, if you trained on some hiring data, it may prefer some candidates from some specific jobs. For example, young males for the programming jobs, and may assume that they perform better there, which is biased. Another problem is copy-paste paradox. I've always told about hallucination problems, that the neural network may start imagining things that is not true. Another problem that it may just start copying something that was already said, like copying retail analytics from the last years, which is also bad. And it's a paradox because we have basically two edges. Like, it can either try to imagine something and start hallucinate, or it can try to not imagine anything and try just copy that what already in its data set, which is also bad. There are some different tools like GitHub Copilot, which was developed by GitHub and OpenAI. It provides real-time coding suggestions in IDEs. It was trained on a lot of lines of code in GitHub, and supports a lot of different languages. But the problem is that it was trained on the GitHub, so there are a lot of code. It may be not secure. It may have low quality. It may be under some copyright, so it is not really good, and it requires a subscription for it to work properly. Another option is code generation mode in ChatGPT. It can generate some code just from natural languages. It can support a lot of languages. It can support like natural languages. It can explain some concepts of what is used, why it is used here. It can explain the code, but the problem is it does not provide some real-time suggestion like Copilot, and it may hallucinate. And because it works with natural language, so it really sensitive to the prompt we are sending here. So, like, from my friend's experience, if he starts swearing with the model, it will start generating better results for some reason. Another study showed that if you will write something like, "My career depends on this task," it will also generate better code for some reason. So you have to actually work on your prompt so it could be better. Another tool is Amazon Code Whisperer, which is mostly used for the optimization of Amazon Web Services. It was made by Amazon Web Services, and its main benefit that it works with it, but it doesn't work so good if you are using something that is not AWS related. Basically, the pros and cons of the AI generated code. It obviously allows to code faster because we can just generate the code. And from some sample studies, it shows that it may increase the speed by 35%. Obviously, it enhances productivity because we are spending less time on such boring tasks. It's just writing the same code, writing the same analysis over and over again, which can be just generated by code. This is already in a lot of other projects. So we do not have to go to the GitHub and to Stack Overflow and find the correct solution. So we are not wasting our time on it, which is good. And also that it can support a lot of languages. Another problem it has that from some GitHub studies that 40% of all generated code contains some vulnerabilities like SQL injection or something like that. And it is much more than usual human written code contains. Again, another problem is hallucinations, which I already mentioned, but another problem with it is that as I said previously, the AI uses its predictions to generate the next prediction. So if it will hallucinate at some point, the error will escalate further and further and further, and the quality of the answer will worsen and worsen and worsen. And from my observation, if it will start hallucination in the beginning of the sentence, the whole answer would be some nonsense. Another problem is legal and ethical concerns. Basically, it's all about copyright claims, so it may use some copyrighted code without any permissions, and just copy it without mentioning that it was copyrighted from some source. This is an example of some vulnerability with SQL injection. Here we can see some query which is used some user input which user can provide, but user can provide some SQL injection here. So it will have access to much more data than we should expect, which is pretty bad, but the AI can generate code like that. And that's basically all I had. Thanks for your attention.
Thank you for your presentation. So let's start the discussion. So who wants to ask something?
Yeah, we have a question. So thanks for the presentation. I wanted to ask you if you tried like solutions that are really really integrating the AI for the code. I mean, like dedicated IDEs like Cursor or CodeLlama or like this kind of things, because I know ChatGPT, like Gemini, and all these AIs, they are like really like chat, but this Cursor and stuff like this, they are really like thinking about the context of your whole project.
Yeah.
So have you tried these solutions, and if yes, is it really like making a big difference?
I haven't tried them in person, but I heard that a lot of them that they're really good, that they allow you that they are actually taking the content of the whole code of the whole project, and they are actually taking your feedback. Like you can swap between different generated answers from it, basically to put likes on dislikes, so it will use the reinforcement learning to make its next predictions better.
I haven't tried it, and I also hear the same that it's really much better, but I never experienced it myself, so I'm curious.
Okay, maybe I have a rather hard question, but you might know something about this. By the way, thank you for the presentation. It was nice. I want to know the techniques that you mentioned, how to train. Do you think it is applicable to the group currently? We have possibility to train, of course, the computers for that, and which method would you think could be applied if you have any ideas now? Maybe not sure, but if you see any parts of your presentation that could be applied to the workflow of the group with respect to coding and software development.
Well, basically, the simplest way to use it would be just using something like GitHub Copilot to make the coding quicker. That's just the simplest solution.
Okay, but if you want to go further, of course, we are already using GitHub Copilot. We are already using some specific bot based on Copilot. So maybe this is on discussion afterward. So thank you.
In theory, this GitHub Copilot can be improved with some with some correct prompt, but I'm not sure if this works exactly for the GitHub Copilot. As I said, it's sensitive to the correct prompt. Like you can write some context of the prompt like that. Maybe that would be
Yes.
if it's possible.
Yes, but this is usually paid. Like in enterprise version, you have something like knowledge base, which you can build. Yeah. Yes. Okay.